Okay, so here we go. Here's the review. Let you know what's on the test, kind of stuff that's on the test. So there'll be one optimization problem, and it's using the stuff from section 13.8, but it's really I took it out of an example in 13.9. So ultimately, the procedure was very similar to what we did in single variable calculus. You're going to have some function of x and y of two variables, and you take the partial of the function with respect to x, and you set that equal to 0, and you take the partial with respect to y, or the second variable, set that equal to 0, and what you get is two equations and two unknowns, and then you can solve for those two variables, the two unknowns being x and y, or whatever the variables are. So that's pretty straightforward. And then there is a second partial test to determine whether it's a minimum or maximum. So you can look at that and maybe write those requirements down. So there's this quantity d, which is the second partial with respect to x times the second partial with respect to y minus the cross partial squared, which doesn't matter which way you do it, you get the same answer. And then you look at whether d is greater than 0 or less than 0, and whether the second partial with respect to x is greater than less than 0 to give you the relative minimums or maximums. So anyway, that's I'm not going to do anything on Lagrange multipliers on the test. Okay, so that's chapter 13. Then we got to chapter 14. And so let's see, what have I got here? So there's no iterated integrals per se, finding the area between two curves by using an iterated integral. There is a problem, find the area under some function f of x, y, or z equals something, and using double integrals. So the idea there is you look at, in the xy plane, what it defines the region. You're going to integrate over the region in the xy plane, and then you've got your f of xy, which is your z function, and then you've got your dy dx or dx dy, depending upon which way you want to do it. And this region is defined by the part of that we're looking for the volume between the xy plane, the part of the xy plane. So, just as an example, let's say we're looking above the area in the xy plane that's this part. So what we do is we'd be integrating in the y direction. We'd have y equals the square root, whatever the radius of this thing is, r. So it would be r squared minus x squared minus, in this case it wouldn't be minus. So since we're only starting at we're just doing this quadrant, so you go from 0 to plus the square root of r squared minus a squared. Now if I went down to here, then I'd have for minus. And my x limits here would be from 0 to r. If I went, say, here, I'd go from minus r to plus r. So, and they don't have to be circular. I mean, they can be triangular. I could I could have something where I'm looking at a something like this, kind of a diamond-shaped region, and trying to think. I just made this up, so hopefully it makes sense. You might have to break this into two intervals, possibly, because you'd have different curves here and here. Yeah, I think you'd have to do it as two integrals. So what you would do is, again, there's some in the z direction, there's some function, but this is the region as you're defining it in the xy plane. So I believe you would have something like this. Let's see, this is the line y equals negative x, and this is the line y equals x plus 1, maybe. I think that would work out. And this would be the line y equals negative x minus 1, because it has a slope of negative 1 with the intercept of negative 1. And then this one would be y equals x minus 1. Actually, this one would be, y equals negative x plus 1. So you got x plus 1, negative x plus 1, negative x minus 1, x minus 1. So those are those four boundaries. So if you were to use this as a region, you would have two integrals. You'd have the integral from y equals x minus 1 to y equals negative x plus 1. So these would be the boundaries, upper and lower boundaries, and then you integrate from x equals 0 to x equals 1, and then you'd have your function f of xy dy dx. And then to do the other side, you would integrate from x equals minus 1, negative 1 to x equals 0. So you go from here to here, and the other integral would be from y equals negative x minus 1 to y equals x plus 1 of the same function, whatever the function is that's defining the top part. So let's just kind of look at the regions. Okay. Also be able to take a integral that's a function of x and y. So this is f of xy, and this is some region in the xy plane. This is dy dx, and convert that to some integral from theta equals something. A lot of times it's 0, and theta equals, it could be anything between 0 and 2 pi. So just some theta equals alpha. And then you'd have the inside integral, which would be from r equals something, r1 to r equals r2, whatever's appropriate for the corresponding region here. And a lot of times the regions are circular regions in the xy plane. So instead of going from negative the square root of, like over here, the first one, negative the square root of something, positive square root of something, if you wanted to do in the entire region here, you could go from, you go from r equals 0 to r equals, say, a, whatever the radius of this thing is. And here you go from theta equals 0 to theta equals 2 pi. If you only wanted to do this part, so if I go back to this original problem here, if I wanted to do this integral in terms of r and theta, I just have to do r goes from 0 to r, and theta goes from 0 to pi over 2. Okay. Now to convert to the f of x y function, you've got these relationships: x squared plus y squared equals r squared. You've got x equals r cosine theta, and you got y equals r sine theta. So you can convert this expression as a function of x and y into r and theta, and then you change dy dx into r dr d theta. And once you've transformed the region to r and theta integrals, and you've changed the function to r and theta, function of r and theta, and you've changed dy dx to r dr d theta, then you can do the multiple integration. So make sure you know how to do that. So it's not just doing the integral. You'll have to convert something involving x and y into something involving r and theta. Okay. Then I'm going to kind of relate it to, I guess it's back to, I mean, it's just another version of this, but maybe a little more complicated. Oh, well, that's not actually true. Okay, so we did talk about surface area. And the surface area equation in terms of x and y coordinates is, we just want to be able to apply the equation and not necessarily do the integral, because the integrals can be kind of daunting. So in one variable calculus, we had, the arc length was the integral of the square root of 1 plus f prime of x squared dx. Now, for surface area, you have, again, this integral over the region, which is the region in the xy plane, and then you don't have f of xy here. You have the square root of 1 plus the first partial of this function, f of xy. So you take partial with respect to x, and you square that, and you add the partial with respect to y, and you square that, and then you multiply by dy dx. So be prepared to have some function. You'll be given, so you're given f of xy, which from there you can get the partials, derivatives, and then given the region, you need to determine the limits. So you need to be able to, instead of just put the region, you need to define the limits appropriately. But you're not going to have to do the integral because it's too complicated. Okay. Okay, so we got the optimization problem. Got the double integral. Got the double integral to find the volume. We've got the polar coordinate transformation. We've got the surface area. And we got one more problem, which is, again, a double integral. So there's no triple integrals on this assignment. But I do want you to be able to show, not necessarily do both orders of operation, but show both order of integration. Both orders, direction orders of integration. So what that means is that, I'll define some region explicitly in the xy plane, which then you can come up with the limits, and they're going to be different depending upon which order I do it in. So there'll be some function f of xy which won't change. Then there will be, so this is something, I'll give you f of xy, and I'll define a region, and then I'll have you do it this way, and I'll have you set it up so that I change it to dy dx. So it's just a matter of writing this region in the two forms. So for example, if you had a circle like this, if I integrated with respect to y first, then the upper curve would be plus the square root of a squared minus x squared, and this would be negative the square root of a squared minus x squared. Now, if I were to change the order of integration, then I'd have a horizontal rectangle. And so for the red case, the upper curve, which would be this one, would be plus the square root of a squared minus y squared, and then this one down here would be the negative the square root of a squared minus y squared. So it's something similar to that, except I'm not going to use circles, but it could be another, I could define the boundaries as something, like a parabola and a horizontal line like that. I could have some linear segments or whatever. And then once you set it up in both ways, there's going to be one way that's better than the other. And you may just have to think about it. I can't tell you enough details so you can't do the problem. But I'm going to tell you that the easy way is going to require integration by parts. So you might want to refresh your memory about integration by parts. And there's going to be an answer here. So you're actually going to have to go through the whole thing. So some of these things you're going to have to set up. And some of the things you're going to have to actually do the whole integration. So there's 6 problems.